This is a introduction to the polynomials video, and we'll start, of course, with something we know: y equals x squared and y equals x cubed. Those are both types of polynomials. They're kind of well, they're the parents of the polynomial family. So a lot of the things we know about y equals x squared and y equals x cubed help us understand all the polynomials. So, and these are a specific type of polynomial because there's just one term, and these are called power functions. So y equals x squared and y equals x cubed is a power function. And even if we have, like, say, a 3 up front, like y equals 3x cubed, that would also be considered a power function because it's just one term. So a polynomial is a collection of power functions added together. Oops, that's one way to think about a polynomial. So that means they're not going to have any polynomials are made up of nice, neat things like 3x, 3x squared, 4, those kind of things. So there's none of these extracurricular stuff like square roots and fractional exponents and exponentials. Those have no place in the polynomial function. So I have 6 functions up here, so I'm just going to run through them, and what we're doing right now is just IDing polynomials. In other words, we're determining whether these functions are a polynomial or not. So the first one, right here, so notice that the first term is 3x squared, that's a power function, plus 2x, that's a power function, and then minus 5, that's a constant. So you can have constants in there, I'll say with constants thrown in. But really you could think of a constant as really a type of power function, just that the power is 0, because you could think of 5 as 5x to the 0 power, because anything to the 0 power is 1. So anyway, so that first one is a power function. We would say yes. I'm sorry, is a polynomial. Right? So we go to the second one down here, and notice we right away see this big square root. So that is not a polynomial because it has a what would be called a fractional exponent or a square root. Now this one's a little bit tricky. The next one, notice when we first see it, we got we have a fraction. So normally we don't think of polynomials as having a variable on top and variable on the bottom fraction. But notice we could simplify this. So even though you could simplify this, you could divide each term by x and you would get something that looks like a polynomial, but this function itself is not a polynomial. So we would say no. Okay? Again, what I was saying is some people might be tempted to go, oh, x cubed divided by x, 3x squared divided by x, and 4x divided by x can all be done, and then it turns into polynomial. But it's not a polynomial because this function actually is not defined at x equals 0. Okay? So, moving right along. The next one up here, this is not a function for not a polynomial for a couple of reasons. The 1 over x would make it not a polynomial because another way to write 1 over x is x to the negative 1, right? So negative exponents and fractional exponents are not a part of polynomials. Notice 3x, that one's okay. That doesn't create a problem. But notice here we also have a fractional exponent up here. So that this is not a polynomial for 2 reasons. How about this next one? This one doesn't look like what we think of as a polynomial with something plus something plus something. But this is a polynomial. It just happens to be, I didn't write a note up here. It happens to be in factored form. So if you could picture this, if you were to multiply this out, you'd go x times x, x times 2, 3 times x, 3 times 2, and then multiply all those terms by 3x. You would end up with something that looks more like this first one. So this is a polynomial. And then finally, the last one, we're looking good at the first term. That's a power function, or a power term. Look at the next one, 3x, that one works. And then we get to this last one, and this is not a power term. This is a exponential, because notice the difference here. the variable is the base and a number is the exponent. On this one, the variable is a constant, and the exponent is, I'm sorry, the base is a constant, and the exponent is a variable. So this would not be a polynomial. Okay? Now, when you're talking about polynomials, one of the ways we classify them, which is really important, is by degree. So the degree of a polynomial just means the highest power. It's the power of the term with the highest power in the polynomial. So if you notice here, this is a second. This power, the power on the exponent on x is 2. Here, the exponent on x is 1. And here, of course, like we said, the exponent on x is really 0, even though there's not x there. So the highest power on x in this expression is 2. So this would be a second degree polynomial. This is not a polynomial, so we wouldn't talk about degree. No. Now this one, so again, a little bit harder to see because we can't actually see the terms of the polynomial. But you have to think about what would happen if I multiplied x times x and then multiplied that again by 3x. So you can see, if you think that through, even without multiplying them out, you can imagine that the highest powered term would be x cubed. Because you'd have x times x, and then that would give me a term, and then I have to multiply that by 3x. So the leading term would be 3x cubed, which means this is a third degree polynomial. Okay, so one skill you need to be able to have is be able to recognize whether something's a polynomial or not, and then if it is a polynomial, be able to discuss the degree of that polynomial. Okay, so now that we know a little something about what a polynomial is, we want to use what we know about y equals x squared and y equals x cubed to try to make some general statements about polynomials in general. So we all know that y equals x squared looks like this, and y equals x cubed looks like this. Okay, so that gives us an idea of what polynomials look like. So first of all, and likewise, things we know about x squared is if there's a negative out front, that basically just flips the polynomial over. The parabola over. If there's a number out front, like y equals 3x squared, that's basically going to make it taller, which makes it end up being thinner. And like we said, if it's y equals negative x squared, then it's upside down, but the same shape. And so there's some general understandings about that. So if I talk about the end behavior of a quadratic equation, so end behavior, that just means what is it doing, what are the y values doing in the end, which means if we're talking about on a graph, we're saying if you go way out to the right or way out to the left, what are the y values doing? So you can see here on y equals x squared that as you go, so if we put a little coordinate grid in here, as you go way out to the right, the y values are just getting bigger and bigger and bigger without bound. As we go way out to the left, so in other words, as x is getting bigger and bigger and bigger negative, the y values are getting bigger and bigger positive. So the end behavior, if we're talking about just plain old y equals x squared, the end behavior, and this is the way we formally write it. So if I want to know what's the limit of x squared as x approaches infinity. So you can see if we say as x approaches infinity, that means that x is getting bigger and bigger positive because it's headed towards positive infinity. So this is asking the question, when x gets closer and closer or gets bigger and bigger, what is x squared doing? And the answer is that it is also getting bigger and bigger. So the answer is infinity. Likewise, we could ask the question, what's the limit of x squared? Which means what is x squared doing as x approaches negative infinity? And the answer here, again, is, well, it's just getting bigger and bigger. So it would be positive infinity. So notice this is saying x is headed out left, y is headed up. This is saying as x is headed out to the right, y is headed up. And that's true of y equals x squared, because the arrow is pointing up in both directions, okay? Now compare that to y equals x cubed. The limit of x cubed as x approaches infinity, and the limit of x cubed as x approaches negative infinity. So if we look at that picture up there, let's put a little coordinate grid on here so we can think about that. So as my x get bigger and bigger, as I'm headed out this way, what are my y's doing? Well, they're getting bigger and bigger also, aren't they? So as x gets bigger and bigger, then my x cubed are also going to get bigger and bigger without bound. If you come back over here, this one's as x heads out negative, if I'm headed towards negative infinity, my x values are, what are my y's values doing? Well, in this case, they're going down, aren't they? So we would say that that's headed towards negative infinity. Now, if we just see for a comparison, if we took a function like y equals 1 over x, and this is not a polynomial, but just for comparison to what we just talked about, if you look at that graph, we know it looks like this. This is just so you understand in behavior a little better. The limit of 1 over x as x approaches infinity, and the limit of 1 over x as x approaches negative infinity. So notice in this case, as x get bigger and bigger and bigger, my y values are getting smaller, aren't they? So as I run out to the right, I'm watching the graph, it's coming down. And it's getting smaller and smaller and smaller. But the limit to there is a limit to how small it can get, because it'll never cross 0. So it'll get infinitely close to 0, but it'll never touch 0. So we say the limit of 1 over x as x approaches infinity is 0. And that's what that limit means, that there is some limit to where it's going. Notice this is saying there's no limit to how big it gets. Same as this. This is saying there's no limit to how big it gets. This is saying that it's getting smaller, but it's never going to go below 0. And likewise, we look at on the left side as x goes out. This time the graph is coming up, but it's never going to get above 0 because it stays negative. But once again, the limit would be 0. So, end behavior of y equals x squared is infinity on the right, infinity on the left. The end behavior of y equals x cubed is infinity on the right, negative infinity on the left. And the end behavior of 1 over x, which is not a polynomial, this is just for comparison's sake, is 0 on the right and 0 on the left. All right. So, now let's go back and, so this is what we know about y equals x squared and y equals x cubed. So notice that if I was to take something like y equals x squared plus 3x minus 5, and maybe even put a 4 out front there, that doesn't change anything as far as the end behavior is concerned. This is still a parabola that's open up. Now it's going to be going to be a different shape because of the 4. It's going to be moved around because of the 3 and x. Obviously, it's not sitting on the vertex is not on the origin anymore. But this is still, as far as end behavior goes, is going to be a positive infinity on the right and positive infinity on the left. So we can say in general, if the a value, remember this is the a value here, if the a value of a quadratic equation is positive, then the end behavior is going to be infinity on the right and infinity on the left. If I have something like this, it doesn't really matter what's happening out here. If I'm just talking about end behavior, notice that the a is negative this time. So now I know that I have an upside down parabola. And if I'm talking about end behavior, it's going to be negative infinity on the right and negative infinity on the left. And again, just for a contrast, I'll write this in proper notation. So this is one way to discuss end behavior, just kind of in words. But the proper mathematical way is to say the limit of, and I'll just call it y, instead of writing the whole thing out. The limit of y as x approaches infinity, so this is on the right, is equal to negative infinity, and the limit of y as x approaches negative infinity, and that would be referring to the left, is also negative infinity. So notice here it's positive infinity and positive infinity because the a is positive. Here it's negative infinity because the a is negative. If we do a similar comparison to cubic, let's say we have y equals 3x cubed plus 4x squared minus 7x plus 2. If you wanted to graph that in your graphing calculator, you could look at it. But essentially what it's going to look like is going to have some dips and valleys, but it'll look very similar to the y equals x cubed. It'll be maybe taller or steeper, but it'll have a little bump here, whereas the normal y equals x cubed it's just flat there and goes up, right? So you can see how this flat thing has been kind of morphed into more of a bumps. So, but again, in the end behavior, even though we have all this extra stuff out here, it doesn't affect the overall end behavior because I'm looking at extremely out to the right and extremely out to the left. So this function is still going to have an end behavior. Whoa, that's too thick. Right there. It's still going to have an end behavior of, let's see, the limit of y in this case as x approaches infinity is infinity, and the limit of y as x approaches negative infinity, so that'd be out to the left, would be negative infinity. It's going up on the right, going down on the left. And once again, if we put a negative out front, so let's say negative 2x cubed plus 7x minus 42, that's going to switch the direction of, it's basically going to reflect it, right? We know that reflects it across the x-axis. So instead of going high on the right and low on the left, this will be the other way around. So what's the end behavior? Come on, write that correctly. Behavior. That would be limit of y as x approaches infinity would be equal to, so as I'm going to the right, it is actually going to go down, and as I go to the left, it's going to go up. So by putting a negative out front and that leading coefficient, it just switches the two end behavior answers around. So then our next thing is to make a connection, and if you play around with the graphing calculator at all, you'll discover that as we put higher and higher powers in this, so we know that a parabola looks like this. If you have and a cubic looks like this, so this is a second degree, here's a third degree polynomial, looks something like this if it's positive leading coefficient. And a fourth degree is going to be similar to the second degree, except for it's going to have some extra bumps in it. So it'll look like that. And if you see a fifth degree, again, it'll look similar to that, but it'll just have some more bumps in it. So it'll look something like that, possibly. And so what we discover is, as far as end behavior goes, all the even-powered polynomials behave like the quadratic, and all odd-powered polynomials behave like the cubic. So just by looking at, so if I see some big old polynomial like y equals negative 4x to the 6th plus 7x to the 3rd minus 4x squared plus 8x minus 3. Okay? So first of all, this is a 6th degree polynomial. We can tell because the highest power is 6. And I notice that the leading coefficient is negative. So that tells me it's been flipped over. And since it's 6th degree, that's an even degree, so it behaves like a quadratic. So if I could jump right to end behavior here now, end behavior, the limit of y as x approaches positive infinity. So as I go out to the right, this thing is going to be going down. And the limit of y as x approaches negative infinity. So as I go out to the left, it's also going to be going down. Because it's really, in the end, behaving just like a negatively coefficient parabola. So just by, when I look at a big long polynomial like this, as far as end behavior is concerned, all I have to do is look at the highest powered term. And I check to whether it's negative or positive, and whether it's even or odd. And just from that, I can come up with end behavior. So another way to say this is polynomials, the end behavior of polynomial is really the same as the power function of the same degree. So in other words, this thing really behaves, whoops, this thing really behaves just like, it's going to be too thick. This thing really just behaves just like y equals negative 4x to the 6th. As far as end behavior is concerned, of course, this will look a lot different than that graph, but in the extreme right and left, this will be doing the same thing as that, so that we say they have the same end behavior. All right. All right, so this video is getting a little long. I think I'm closing in 20 minutes here, so I think I'll stop this and post it, and then I'll continue on in the next video because there's still a lot of things to talk about with polynomials. So, but this is a good video to get you started.